Hello, everyone, and welcome to another episode of Noeri Daris. Today we'll be going through thermochemistry. We'll be going through all four laws of thermodynamics, and enthalpy gives energy, entropy, etc. So stay tuned, watch the video till the end. Let me know if you have any questions or any concerns that I can go through. So, first off, we have the zeroth law. The zeroth law is that when two systems are in thermal equilibrium, their temperatures are the same. So you have system A, system B. They're both in thermal equilibrium. They're both the same temperature. But here, bear with me. What if A had more temperature than B? So energy would flow from A to B to make sure the system is at equilibrium. Both the system and the surroundings form thermodynamic universe. Okay, now to go through the first law of thermodynamics, which you probably heard a lot, is the total energy of the universe is constant. Energy cannot be created nor destroyed. So let's for instance say the whole universe is like 5, all right? These 5 will be uh, it's not created, but I mean transformed into another form of energy, and it's a cycle. But like the same 5 are constant, but they will just like change forms, shapes, take on different identities, I would say. So energy flow surrounding into the system, right? Let's say the surrounding is A, and then the system is B, all right? And then A had more energy in it, so and then B didn't have as much energy, so it would flow from this is the surrounding to B, which is the system, thus increasing the system and decreasing the surrounding. And the same, it's also the other way around. If the system had more energy, it would flow from the system into the surrounding, thus increasing the system energy and increasing the surrounding energy. Next we have is enthalpy. Enthalpy is the reaction of the bond being broken or formed, meaning that energy is either released or absorbed. Energy is released when bonds are formed, alright? And then bond is broken, energy must be put in, effort must be put in order to bring and connect and bond these energies in. Yeah. So exothermic reaction is when bonds are formed, energy is released from the system, and enthalpy is negative. Enthalpy is negative when bonds are formed. Right? So you form the bond, alright, and it's negative. And then bonds are broken, so you need to put energy in order to break it. So in order to break the bond, you need to put energy. Endothermic reactions are like bonds are broken and energy is absorbed from the surrounding into the system. Okay, so you had so in terms of endothermic reaction, so you already formed a bond, all right, but now you want to break it. So in order to break the bond, energy needs to be put in and taken from the surrounding where energy was released in the previous exothermic reaction, right? So exothermic, enthalpy is negative. Endothermic, enthalpy is positive, all right? STP is 298 Kelvin and 25 Celsius, 1 atm pressure and concentration of 1 molarity. So a standard heat of formation is the amount of energy required to make 1 mole's element in its natural state. But there's an exception. Exceptions are diatomic molecules such as oxygen and H2 because that's how they exist. Okay, like they exist in diatomic pairs. Okay, so when the heat of formation is positive, energy input is required. When heat of formation is negative, energy is given off. So also remember, there's a little bit of correlation here. Bonds are formed, you know, energy is given off or released. Bonds are broken, energy needs to be put in. Here, it's kind of the same. Now we have the second law of thermodynamics. Second law of thermodynamics is pretty simple. It says that disorder of the universe increases in spontaneous process, and that process leads to maximum disorder. That the universe is always looking for disorders and spontaneous reactions. So the second law of thermodynamics, in which we measure disorder, is called entropy, and it's delta S. Entropy is delta S, all right? So liquids have more entropy than solids. I mean, liquid have more uh, disorder, or more prone to disorder than solids, all right? And gases have more entropy than liquids and solids. So, and like I said, the natural overdrive is to increase entropy, increase disorder. The universe wants to increase the disorder. Um, why would you say the liquids and the gases have more entropy? Because I want you to imagine this in your head. Can you, like, you can hold a water bottle in your hands, all right? It's not gonna really do something. It's not gonna slip out of your hands unless you let it. But like go to the beach and try and hold water, all right? And then can you contain that water without it slipping, without it increasing disorder, leaving your hands? Try also doing that with gases. It's gonna be impossible with gases, to contain it. If randomness increases during the reaction, entropy is positive. So increasing the randomness increases entropy and making it positive. If randomness decrease, entropy is negative. So randomness increase, entropy positive, randomness decrease, entropy is negative. So now, let's say you want to decrease. How do you approach a decreasing entropy question? So if you're going from gas to liquid, that's decreasing randomness. It means you're decreasing disorder. It means you're making things more stable. And then you got the third law of thermodynamics, which is called absolute zero. It's a really simple law. It says that absolute zero is to be in the state of absolute zero, meaning zero temperature, zero randomness, zero kinetic energy, thus a solid. All right? Bring a random object, a pen for instance, in front of you. Is it moving? Is there any disorder? Is there any entropy? No, it's just a solid. It's just sitting there. Okay? As you can see here, absolute zero. No temperature, no nothing. Then you got Gibbs free energy. It tells us about the spontaneity of the process, whether it's going to be spontaneous or not, whether it will happen on its own or not. Right? So the equation for that is delta G, which is Gibbs free energy, and then delta H, which is enthalpy minus temperature times delta S, which is entropy. So a change in Gibbs energy is the change in enthalpy and change in entropy and temperature. So all these factors have an effect on whether the reaction going to be spontaneous or not. If delta G is negative, reaction is spontaneous. So if delta G is negative, the reaction is going to happen on its own. If delta G is positive, the reaction is non-spontaneous. It's not going to happen on its own. Lastly, I formed this table in order to just predict kind of the outcomes. So if the enthalpy was negative, right, so a bond is formed, okay, and then entropy was positive, it means there is an increase in disorder, and just delta G negative, meaning that reaction is spontaneous, so the reaction will be spontaneous. Right, delta G is negative. We already said if it's negative, spontaneous. Now, what if enthalpy is positive? It means bonds are broken. You need energy. And then here, randomness is increased. So in that case, you have two options. When temperature is high, and meaning it's like negative, the reaction is going to be spontaneous. And when temperature is low, it's positive. It's going to be non-spontaneous. Here we're talking about Gibbs energy, because temperature here is the determining factor when enthalpy is positive. All right, what about when enthalpy is negative? It means bond is formed, energy is released, and but here entropy is decreasing. It means it's going, for instance, from gas to liquid or liquid to solid. So when temperature is high, the other way around now, um, it's positive, so non-spontaneous. And when temperature is low, it's negative, it's spontaneous. A spontaneous reaction will occur. So positive enthalpy, right? Bonds are broken, and then here randomness, and here positive. So everything doesn't work out to be a spontaneous reaction. So here you need to put in energy, here you need to uh, put in energy because you're also changing phases. So the reaction is going to be non-spontaneous. So exergenic and exothermic reactions, and when products have less energy than the reactants, you get a negative um, uh, delta enthalpy. You get a negative enthalpy. All right, it's basically I'm sure you guys have seen this before. This is an exothermic reaction, and then the other way around is the endothermic reaction. Delta G is positive because products have more energy than reactants. And that's it. Thank you so much. This was a quick lesson on thermochemistry. Please let me know if you have any questions or any concerns. Watch a video, share it. Thank you so much.